Welcome to this video. We're going to see another problem involving power production, this time with solar power, and then we'll move on to hydroelectric pump storage systems. A town consists of 120 houses. It's proposed that solar panels be used to provide hot water to the houses. Solar panels capture solar radiation from the sun, and they use it to heat up water. The following data are available. We've got the average power needed per house to heat the water. We have the average surface solar intensity in the town, and we have the efficiency of the energy conversion within each panel. Now we have to calculate the minimum surface area of the solar panels required to provide the total power, which would be needed to heat all of these houses' water. So we're looking for what? We're looking for the area. We're going to write down the equation that has area. It's the one with intensity and power. Now, before we can solve for area, we're going to first need power. And in this case, it's the input power. Why is it the input power, not the output power? Well, the input power is from the sun. The output is the heating of the water. So the hot water, that's the output power. The intensity formula pertains to the intensity of sunlight. Therefore, this is the power of the sunlight, and that's the input, not the output. Now, we're going to find the input power value from the efficiency equation, because you can't solve for area until you have both of these two things. We're given intensity, right? Here it is, it's 650, but we're not given power in, so we find it from this equation over on the right side. So just to recap, we're going to find the input power from the sun using the efficiency formula. We'll plug in that value here, and then we'll find the area, which is the unknown. So here's that efficiency equation. The output power that we need is going to be 650 per house times the 120 houses. The efficiency again is 0.18. We solve for Pn, and the answer is this. So now we plug that Pn value right here in the intensity equation. We know the intensity of the light. We solve for area, and the area that we need would be 144 meters squared, which is quite a large area. So you can see that maybe this is not such a practical approach. Here's our final problem. The tank of a pump storage system is 50 meters deep and has a uniform area of 5 times 10 to the 4 meters squared. So we're given the depth and area. We could go ahead and find volume if we wanted, but we'll hold off. The height from the bottom of the tank to the turbine is 310 meters. That means when the water drops out, it's going to fall 310 meters. The density of the water is 1 times 10 to the third kilogram per meter cubed. So we're given density, rho. What's the formula for density? Oh yeah, it's rho equals mass over volume. First, we show that the maximum energy that can be delivered to the turbine by the falling water is roughly 8 times 10 to the 12 joules. Okay, so we have to show that this is the energy delivered by all of the water when it falls. The energy is gravitational potential energy. That's what the water has because of the height. And it's going to fall some delta H. Now, we're not given the mass of the water, so we have to use the density equation to find the mass. If we isolate mass, we see that mass simply equals rho times volume. So I'm going to write the equation again for energy, but I'm going to replace mass with rho times volume. We know those four things. Rho is this. Volume is 50 times the area. G is 9.81, and delta H, well, that's 310 because that's how far, that's 310 because that's how far the water falls to the turbine. So you calculate, and this is what you get. We can round this to 8 times 10 to the 12, 8 terajoules, and thereby confirming the answer that we set out to show. Part B says the flow rate of water in the pipe is 400 meters cubed per second. Calculate the power delivered by the falling water. Now, meters cubed right? That's a volume. That's a meter by a meter by a meter. So that's a volume. And meters cubed per second means we've been given the volume per unit time. We've been given V over T. So we're going to use V over T to find the mass that flows per second. Now, I'm going to write an equation down. Mass per second is equal to volume per second times mass per volume, because the volume would cancel, leaving us with m over t. So we're going to plug in volume over time, which is 400, and mass per unit volume, that's just the density, kilograms per meter cubed. M over V is rho. So we calculate the mass per unit time, and we get this. This is how many kilograms flow by per second. Now we can finally find the power. The power is given by the formula energy over time. And what's the energy? Well, again, it's gravitational potential energy that's being converted. So I'm going to break up G times delta H over here, and what remains is M over T. So now we have three things that we know. M over T is given. M over T we just found, it's 400,000. G we know, that's 9.81. And delta H is also given, that's the same 310. So you solve to get your answer. 1.2 times 10 to the 9 watts, or we could write that as 1.2 gigawatts.